Projectile motion is simply the motion of an object that has been launched into the air. Now we want to look at the situation where an object starts out at some angle. When a projectile is launched at an angle, we just mean that it is not starting out moving horizontally with respect to our reference surface. For example, when you kick a ball up into the air, like a football or a soccer ball, the ball does not move straight up, but it doesn't move straight out either. It's somewhere in between, which means that the ball leaves the ground with some x component and some y component to its velocity. The ball will travel in the vertical and horizontal direction until it reaches some peak before coming back down with a motion that is a mirror of what it traveled up at. Say we are hitting a golf ball off of the tee with some initial velocity. When we hit the ball, it is not completely in a horizontal motion, it's not completely in a vertical motion, but at some angle relative to the ground. The ball does not continue to follow the initial velocity vector because gravity immediately has an effect on it and accelerates the ball towards the ground. Eventually, the ball reaches a point where its initial velocity is not enough to keep it moving in the upwards direction, and it begins to fall back to the earth. We call this the y maximum, and it occurs halfway between the starting and ending locations. The ball then begins its descent back towards the ground, and the result is a beautifully symmetrical parabolic path that we can describe in 2 dimensions. In order to solve problems with this type of situation, we need to define a few points. We already have an initial velocity, and we have defined the angle as theta. We also have the height of the parabola, called the y max, or delta y. We can measure the distance from start to landing as delta x. This is our range, or our change in horizontal position. We can also say that the time it takes for the ball to land after it has been hit is the total change in time. That symmetry comes in useful here because we can conclude that the time it takes for the ball to reach the y maximum is half the total time and half the total x distance. Therefore, the time it takes for the ball to reach y maximum is half of the total time. Likewise, the distance the ball travels in the horizontal at the point that it reaches y maximum is half of the total x distance. So we launch this projectile at an angle at some initial velocity that we can break down into its x and y components. We can bring this vector down and form a right triangle with the initial velocity vector and the horizontal ground with the launch angle theta as one of our angles. From here we can use trigonometry to determine the x and y components. The initial velocity in the x direction is found using the adjacent over hypotenuse function, which is cosine. So the initial launch velocity times the cosine theta gives us the initial velocity in the x direction. The initial velocity in the y direction comes from the sine function, since it is the opposite leg from our angle theta. So the initial launch times sine theta gives us the initial velocity in the y direction. So these values can be used in our kinematics equations. You can actually use these if your projectile is launched horizontally if you like, but since the cosine of 0 is 1 and the sine of 90 is 1, it is just one more step we really don't need to add in. So let's think about why that is for a moment. There is no acceleration in the x direction, so its velocity is constant. In the y direction, acceleration is causing the ball to slow down until it reaches the max at the top of the parabola. Here it will stop moving up in the y direction before beginning to move back down with an increasing speed towards the ground. In keeping with the symmetry of the motion, the ball actually hits the ground at an angle equal to its launch angle. Because of this, the final velocity ends up having the exact same x component as the initial velocity. The y component of the final velocity, however, is in the opposite direction as the initial y component. So to find the final y component, we just need negative of the original equation. So this gives us a pretty good cheat sheet of those kinematic equations and how we can use them to describe projectile motion. So say we have a fireworks shell that is shot into the air with an initial velocity of 70 meters per second and an angle of 75 degrees above the horizontal. Calculate the maximum height at which the shell would explode. So we know our initial velocity, we know the angle that we're launched at. Acceleration due to gravity is always negative 9.8 meters per second squared. And since the shell stops at the top of the trajectory and explodes, we can say here that the final velocity of the shell is 0. We are looking for change in y, so at this point we really only need the y component of the initial velocity. We find this by taking the 70 meters per second initial velocity times the sine of the angle 75. This gives us 67.6 meters per second as the initial y component of the shell's velocity. Now we are wanting to know the height that the shell reaches. Since we know final and initial velocities along with the acceleration, the best equation to use here would be the velocity squared. First, we need to do a little rearranging and solve for delta y, but then we can add in our known values. Remember, we are looking for the vertical height, so we need to use the vertical component of our initial velocity in our calculation. All of that, and we end up with a height of 233 meters. Another question we can ask is how long will it take for the explosion to occur after launch? We just found the height of the explosion, so we can use our change in y equation that includes both velocities. Rearranging for time and plugging in all of our knowns finds the shell explodes 6.90 seconds after it's launched. Finally, how far does the shell travel horizontally before it explodes? Remember, our x motion is dependent only on the final velocity and the time, since there is no horizontal acceleration. Just like we did with the vertical motion, we need to determine the x component of our initial 70 meters per second. Initial x velocity is equal to the initial velocity times the cosine of the angle 75 degrees, and it turns out to be 18.1 meters per second. This is both our initial x and final x velocity, so we can use this in our x displacement equation to give us the shell exploding 125 meters in the horizontal direction. So when a projectile is launched at an angle, calculations in the horizontal direction must be done with the x component of the initial velocity. The x component is found using the cosine function. Calculations in the vertical direction must be done with a y component, and this is found using the sine of the angle. Also remember that the y component of the velocity at the beginning of the motion has a positive value, while the y component at the end of the motion has a negative value.